Relax. In this example, I'll be talking about the required energy for water to first rise in temperature and then change from liquid into gas. So this amount of energy can be divided into two parts. First of all, it is the energy required for water to rise in its temperature to the boiling point of 100 degrees. So let's say that the water I'm taking into account, the amount is 5 kilograms, and the initial temperature will be 50 degrees Celsius. The temperature I have to get to is of course 100. And what I want to do is I want to get all of this water to boil. So what is the entire energy required for this water to boil? Well, first of all, it has to change from 50 degrees to 100 degrees. And the second part, and actually even more energy intensive part, surprisingly, is the energy required for it to turn into a gas. So vaporization. So I have these two pieces of information, and these two pieces of information talk about slightly different things. Namely, the first one is denoted as C. So this might look similar, but it's actually a different letter. This is L below. So this one on the top is C, and what it talks about is the specific heat of water. It's the amount of energy in joules that's required for water to rise in temperature per kilogram by 1 degree Kelvin. And of course, Celsius and Kelvins, the distance between individual unit degrees is same, although Kelvins start at minus 273 degrees Celsius, whereas degrees start at Kelvin of 273. So, what I have to take into account, I want to look at the entire energy required for the water to change from 50 degrees of liquid water into gas. So what is the entire energy? As I said, first I have to switch from 50 to 100 degrees. I have to raise it. That's thanks to the specific heat, which specifies basically specific heat. What it is I take a particular amount of water in kilograms, then I specify how much is the temperature change by how many degrees, Celsius or Kelvins, both units apply here, and I have to mention what the specific heat of water is, which I have it here around 4.2 kilojoules. Then the second part, so let's say this is the specific one, and let's say the second one, the latent one, well, it does not require temperature change because it only talks about the energy required to change from liquid to gas. Therefore, it's just the M times L, which is a latent heat. It's called latent heat, and as visible here, it's around 2,260 kilojoules per kilogram. So it's far more per kilogram. And what it talks about is basically the energy required for each kilogram of water to change already at the boiling point, not even rising in temperature, but just to change from one way of being into the other, from water into gas. So basically the entire energy consumed is both of these together. It's first of all the change in temperature to the 100 with this constant multiple of 4.2 kilojoules, and the second part is M times L, where again the same kilograms of water, but L is the amount of energy required for each kilogram to change into gas, which is the final state that the problem asks about. Just to repeat, it asks about the rise in temperature to become a gas. So it asks about the total energy required for the water to rise from 50 degrees and become a gas. So first of all, it has 5 kilograms. So I start inputting into this equation I created here in 5 kilograms. The delta T is the rise in the temperature for the boiling point of water is of course 100 degrees. So the change is 50. And then I multiply by C. C is 4.2 thousand because it's kilojoules. So 4.2 times 10 to the 3. And that's the specific heat required for each kilogram to rise by 1 Kelvin or 1 degree Celsius. Then plus that, I add again the 5 kilograms. I don't use the units because at the end I know that all of this will add up and be in joules because it will be the energy required. The second part, and I'm by the way already getting all the way to the finish of this process of calculation. The second part will be the mass times L, and L is the latent heat required for each kilogram to turn into gas, 2260 kilojoules. So 2260 times 10 to the 3 again. And of course, this can be further rewritten. Well, 5 times 50, that's 250, times 4 is 1000. So it's 10 to the 3 times 2. So this is 1000, 10 to the 3. This is another 10 to the 3 times 2 plus this entire thing can be written as 1100 and actually this is 260 times 5, which is 1300, so it's 11,300 this together times 10 to the 3 joules. And it is visible that far more energy was used for the transition from liquid to gas than for the rise in temperature, straight here. So I can continue by isolating 10 to the 3 once, or there's more ways to do it. Well, I can isolate 10 to the 3. I can get 2000 plus the 11,300. But this is just the final calculation and work with numbers. Joules. And this gives 13,300. So times 10 to the 3, of course. So it's 13,300, or in other words, 13.3 times 10 to the 3 times 10 to the 3, so times 10 to the 6 joules. So this amount of joules will be required for the water to first rise in temperature all the way to the boiling point and then boil into gas.